Our next goal is to understand how arrays and pointers behave with respect to each other. What is the address of an array? An array stores multiple elements. What is its address? So let's start with an example. Let's say we have an array of integers, and I'll declare it right here, and I'll initialize it in the same step. Let's put in some numbers: 6, 2, -4, 8, 5, and 1. Notice I didn't put a size here. The size is automatically determined because I'm initializing the array right here. 1, 2, 3, 4, 5, 6 elements. I could have also put that 6 in there. It's totally up to you. I'll take it out to show you that this works without putting the number there. Let's start by simply printing out elements of this array to remind ourselves how to do so. So if I wanted to print out the elements, so array contains all integers, so %d, %d. I'm not going to print them all out. I'm just going to put a ... and then the last element. So it's array of 0, that's the first element. Array of 1 is the second element. And then I want to just print the last one. So that's array of 5. All right. So far, so good. What are the memory locations of all these elements? Print those out as well. These are stored at, and memory locations are printed with %p, 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 and %p. And how do I get the address of where array of 0 is stored? I put an ampersand in front of it. So ampersand array of 0 gives me the address of array of 0. Ampersand array of 1 gives me the address of array of 1. And ampersand array of 5 gives me the address of array of 5. So that's enough for now. Let's simply run this code. Compile and run step by step. My array is declared, so there's array of 0 all the way to the left, array of 1, array of 2, all the way through array of 5. And all the values 6, 2, -4, 8, 5, and 1 got put into it. Next, we get to this printf statement that says the array contains the values 6, 2, ... and 1. And next, we're going to print out their addresses. They're stored at address FFE8. If you look at the visualization of the memory strip, you indeed see that array of 0 starts at FFE8, array of 1 starts at FFEC, and array of 5 starts at FFFC in this particular visualization. So now we understand where the individual elements are stored. What were to happen if we printed array all by itself? Let's check it out. Not array of 0 or the address of array of 0, just array. What does that give us? We don't even know what to print that with. Let's start with a %d because it holds integers. So we just put array itself there. What is that? Let's see if this compiles. Well, we get an error message. It says format specifies type int, but the argument has type integer pointer. So it claims that array itself is a pointer to an integer. And that's something very special about how arrays are stored in memory. Array, the variable array itself, actually holds the address of where array starts. So the array itself is printed with a %p because array holds an address. Let's compile and run this. So here's my array. The array contains all these numbers. They're stored at all these locations. And now we're printing out array itself. Array is FFE8. So the variable array itself holds the address where array is stored, namely where array of 0 starts at FFE8 in the visualization that you can see on the screen here. In other words, I'm going to take this out here, but array is equal to the address of array of 0. I can't really put that in here. I'm going to put that in a comment because that's not a statement that we're going to actually use. But I'm going to put that in a comment here. Array equals the address of array of 0. So let's declare some pointers. call it PTR, and it's a pointer to an integer. It holds an integer location. I can now put array into that pointer. So PTR equals array. PTR now holds the address of array, which we know is also the address of array of 0. So if I have a second pointer, PTR2, and I say PTR2 is equal to the address of array of 0, they both hold the same address. Both PTR and PTR2 hold the same address. I'll demonstrate that to you by running this code. We have the array declared, the pointers are declared. So far they don't contain anything. We're printing out the array, and now we're saying PTR equals array. So watch what happens to PTR, to what's stored in PTR. It's updated with FFE8, which is the location where the array starts. Next, watch what happens with PTR2. It's updated with the same address, FFE8, the address of array of 0. The address of array of 0 is the same thing of the address of where the array starts, and that's what's stored in array. So it's actually very smart. The computer stores in the variable array simply where the whole array starts, and from that, it can do math to figure out where array of 0, array of 1, array of 2, and so forth are stored by simply knowing how much space is needed for each individual element of the array. Because the computer knows that we're storing integers and it knows the size of each individual integer, it knows where array of 0 is, where array of 1 is, and so forth. It does what's so-called pointer arithmetic in order to figure that out simply by storing only where the array starts in memory. Let's check that out a little bit more carefully. So first of all, we can dereference this pointer PTR. Remember, it points to where the array starts, which is also where array of 0 is stored. We can dereference that. And what does that do? That gives us access to what's stored at array of 0, and we can change it. Let's put a 10 in there instead of that 6. And let's run that. Step by step, I'm going to step through very quickly through the first instructions. Now here we get to star PTR equals 10. So PTR itself doesn't change, but what's stored at the location FFE8, which is array of 0. So watch array of 0. It changed to 10 with this instruction. Let's do a few more things. So not only can we change that, we can do so-called pointer arithmetic. It turns out PTR plus 1 increases the pointer to the next memory location in what makes sense. So the next memory location from the point of view of PTR, because it points to an integer, is the next integer. So not exactly the next memory location, but the next integer that starts after the first integer is all over. I'll show that to you in the visualization. So when I dereference PTR plus 1, I'm actually accessing array of 1. Let's put a new value in there. Let's put a 5 in there. And let's run this and take a look what happens. I'm going to step through all this first rather quickly. Again, here I'm updating what's stored at the location that's stored in PTR. So I'm updating array of 0 and putting a 10 in there. Next. Notice that array of 0 occupies 4 memory locations in my visualization. Array of 1 also occupies 4 memory locations. What happens when I add 1 to PTR, the address of array of 0, I get moved to the address of array of 1. So I'm not just adding 1 to the hexadecimal address, but I'm hopping over to the next integer. The computer does pointer arithmetic. It figures out that you're not really interested in simply adding 1 to the memory location, but rather you're interested to moving on to the next integer, which will be array of 1. So watch what happens at array of 1. That 2 changes to a 5. So I was able to update array of 1 to a 5 using pointer arithmetic. So let's do that again. This time, let's update PTR plus 2. What's that going to give me? PTR itself was array of 0. PTR plus 1 is array of 1. PTR plus 2 is going to be array of 2. And let's put in a negative 1 there. Let's quickly compile and run. Quickly stepping through the first few instructions. Here we are updating array of 0 by dereferencing PTR. Array of 0 gets the value 10. PTR plus 1 points to where array of 1 is stored. By dereferencing that, I'm changing the value 2 to 5. And next, PTR plus 2 points to array of 2, and I'm updating that value with a -1. We can do this differently as well. We actually don't need this pointer PTR at all. We could have simply worked with the variable array, because PTR, an array, are the same thing. An array is simply the address of array of 0. Array itself is the right address to work with. I could have accomplished the exact same thing by simply dereferencing array. Since array itself points to array of 0, array dereferenced points to what's stored at array of 0. And for example, I can update that with a 3. Similarly, I can look at array plus 1, which is the address of array of 1, dereference that, and put a new value in there, say 5. And similarly, I can do this with array plus 2, and array plus 3, and array plus 4, and so forth. Maybe not a -1. Let's put different values in here. How about the 3? And then how about here we put a 10, and this time a 99. So the values are different from what we did before. Let's compile and run. We go through all this. This we already looked at, but now we're looking at array dereferenced. Array itself is simply a pointer to array of 0. When we dereference that, we have access to array of 0, and we're going to put a 3 in there. So watch what happens at array of 0. A 3 shows up. Array plus 1 is a pointer to array of 1. By dereferencing that, we're going to put a 10 in there. Array plus 2 is a pointer to array of 2. By dereferencing that, we're putting a 99 in there. So that's another way to access all these memory locations. Finally, I want to show you a little bit more pointer arithmetic. We can do something like this. We can look at PTR, which, as you remember, is simply a pointer to array of 0. So it points to array of 0. It's the address of array of 0. We can say PTR plus plus. What does that do? It increases the address stored in pointer by 1. But again, by 1 in what makes sense. So it points to the next integer. From pointing to array of 0, therefore, PTR now points to array of 1. So if I dereference the new PTR and put a 7 in there, then that 7 will show up in array of 1. We better take a look at that. We're going to very quickly move through all these lines until we get here. So we're about to complete the instruction PTR plus plus. So watch PTR. It currently has the value FFE8, which is the address of array of 0. By completing PTR plus plus, PTR got updated to FFEC, which is the address of array of 1. So we moved the pointer over by 1 integer to the next integer. Therefore, when we dereference PTR now, we're changing array of 1. So watch what happens to array of 1. The 10 got replaced with a 7. Let's do that one more time. We can also do something like PTR plus equals 3. Now we're adding 3 to PTR. PTR currently points to array of 1. By adding 3 to it, again, it skips by integers. So from pointing to array of 1, it's going to point to array of 4. When we then dereference this new pointer, we can put, for example, an 8 into array of 4. Let's run this. And again, I'm going to skip over all of these instructions until we get to the ones that are new. So I'm about to execute PTR plus equals 3. Currently, PTR has the value FFEC, which is the address of array of 1. Watch what happens in the next step. Watch PTR. PTR got updated and now has the value FFF8. FFF8 is the address of array of 4, just like we predicted. And now we can dereference that address and change array of 4. So watch what happens at array of 4. Array of 4 changed its value to 8. And the program terminates. So that was a lot to swallow. This is called pointer arithmetic. It's really powerful and useful, and it'll take a while to get used to. So please go ahead and play around with the code. Play with these pointers, add things, subtract things, see what happens. You need to play with this code.